In this video, we're going to be talking about inverse relations. Our notation, first off, the inverse of a relation R is written as R with a little -1. And again, this is not R to the -1 power, although it looks like it, it's just the notation we use. To find the inverse of a relation, it's very simple. You simply switch all x's and y's, or you switch your inputs and your outputs. They don't have to be x's and y's, they might be p's and q's, but you switch your inputs with your outputs. One-to-one relationships. A relation is one-to-one if it and its, that's no apostrophe there, if it and its inverse are both, very important, functions. And a reminder, what we mean by a function is each input has a unique output. Now, when we flip it around, if still each input has a unique output, then it's going to be a one-to-one. So therefore, if we have a relation, let's work some examples. For your original relation, here are your points for your original relation. Then the inverse of that would be simply -2, +1, 4, 2, -1, +3, and -2, +4. Reminder, the original here is a function because each x has a unique y. There's no duplicates. However, there's a problem with the inverse. -2, +1, and -2, +4. -2 is paired with both. So R is a function, yes. Is R inverse a function? No. So is it one-to-one? No, because both are not functions. The next one, our original function is 1, 5, 1, 6, and so on and so forth. So therefore, the inverse of this relation would be 5, 1, 6, 1, -4, 3, and 9, 4. Now let's do our inverse relation first here. 5, 6, -4, 9. There's no duplicate. So therefore, our inverse, yes, is a function. However, is your original relation a function? And there's an issue here. 1 is paired with both 5 and 6, so the original is not a function. So therefore, again, no, this is not one-to-one. Number 3, 0 is paired with 6, 11 is paired with 6, 1 is paired with 2. That's your original relation. So therefore, the inverse, instead of 0 paired with 6, 6 would be paired with 0. Instead of 1 paired with 2, 2 would be paired with 1. And then instead of 11 being paired with 6, 6 would be paired with 11. The original function, or the original relation, is yes, a function, because none of these x's are paired with more than one y. However, I have an issue here, 6, 0 and 6, 11. When I flip that around, the inverse will not be a function. So again, no, this is not one-to-one. Horizontal line test. Now let's recall that the vertical line test is used to determine if a relation is a function. It tells me, are there any x values that's paired with more than one y value? So this would not be a function, because if you hit a vertical line through more than one point, it's not a function. The horizontal line test now is used to determine whether the inverse would be a function as well. Both the relation and its inverse must be a function in order, again, to be one-to-one. So it would have to pass the vertical and it would have to pass the horizontal in order to be one-to-one. Let's work some examples. Number 4 is a function, because if you draw vertical lines, you never hit more than one point. If you draw horizontal lines, you never hit more than one point. So therefore, is this a one-to-one function? Yes, it is. The next one, number 5, is a function, because the vertical line test, you never hit more than one point anywhere on that graph. However, if you draw a horizontal line, notice just with that one horizontal line, I hit 3 different points. So this is a function. Its inverse is not a function, so therefore it would not be one-to-one. Okay, so if inverse functions, if we do have a function has an inverse, then we have a special notation for that as well. The same way that R and R inverse we showed you a while ago, if the inverse of a function f of x is written as the same way, the little -1, f inverse of x is how you say that. Here's the steps for finding the inverses. If you're dealing with f of x's, replace it with y. They mean the same thing. And then you do the exact same thing. You switch your x and y. You solve for y, and then you rewrite it as f inverse of x. So let's try one. Number 5, find the inverse. So your function is y equals 5x. So therefore the inverse would be x equals 5y. Next step, you simply solve that for y. We're going to get rid of this 5 by dividing. So you have y equals x over 5, and you are done. The only thing that's left to do is replace y with f inverse of x. So you now have is x over 5. So here's your original function. Here is the inverse of that function. Number 7, you have y equals x minus 7. So its inverse would be x equals y minus 7. All you have to do to get y by itself is to move the 7 over. It gives you an x plus 7 is equal to y. And you can now replace y with f inverse. So f inverse of x would now be x plus 7. And again, what this does is if your original function, you can check this. Your original function, if you were to plug in 7, you get 0. What about your inverse function? What if you plugged in 0? What would you get? 0 plus 7, you would get 7. So that's what a function and an inverse does. If it switches your inputs and outputs. Number 8, you have y equals x minus 8 over 3. So the inverse of that would be x equals y minus 8 over 3. To get rid of the 3, we're going to multiply. Since the whole side is being divided by 3, gives you 3x equals y minus 8. We now move the minus 8 over and you get 3x plus 8 is equal to y. So now you can replace that with f inverse. The f inverse would equal 3x plus 8. Number 9, your original function is y equals negative 2/5 x plus 1. So the inverse of that would be x equals negative 2/5 y plus 1. Move the 1 over, that'd be x minus 1 equals negative 2/5 y. To get rid of negative 2/5, you multiply the other side by the reciprocal, which would be negative 5/2. You can distribute or you can leave it like that. So we can now write it as f inverse is equal to negative 5/2, and I'm just going to leave that x minus 1 in parentheses. Number 10. Now this was a little bit different. It gives you f of x and it gives you a domain restriction. The reason it gives you a domain restriction is if you graph that whole thing, x squared minus 9, it would look like this, which is a function. However, it would not have an inverse because it does not pass the horizontal line test. However, if you restrict it, now this is what you have. It passes the vertical and the horizontal line test, so it would have an inverse then. However, here's what I want you to do. Take this domain, plug those values in and get a range. What would y equal? If you plug in 0, plug in 1, plug in 2, you get values greater than or equal to negative 9. That would be your range. And you could also find that from a graph. And there's a reason I'm showing you that you need to do that first. And I'll show you in just a second. So now your function is y equals x squared minus 9. The inverse would be x equals y squared minus 9. Move the minus 9 over. You now have x plus 9 equals y squared. To get rid of a square, you're going to do plus and minus the square root of x plus 9 is equal to y. Now let's think about that though. If y is greater than negative 9, plug in negative 9 plus 9 gets 0. Plug in negative 8 plus 9 gives you a positive and a positive. If that's the case, this answer will always be a positive value. So we don't have to worry about the whole plus and minus anymore. That's going to be your new, because we want, well, let's write it like this. Let's go ahead and write our original domain was this and our original range was this. So now what is the domain of my new function and what is the range of my new function? If you remember, when you find an inverse, it switches your domain and range. So therefore, your new x values are always going to be greater than or equal to negative 9, which was the old y values. So that's your new domain restriction that you're going to write with this. And as well, you don't have to write this, but you could, your y values, we want now to be greater than or equal to 0, which was your old x values. So it switches your domain and range. And if we want our y values to be greater than or equal to 0, we've got to get rid of this whole plus and minus stuff. Because if we put that minus, that would give us y values less than 0. So my inverse function, f inverse, is going to equal the square root of x plus 9. Number 11. Step number 1, take out f of x, put in a y. X plus 4 to the third minus 6. Let's switch them. X equals y plus 4 to the third minus 6. Move the minus 6 over. You now have x plus 6 equals, it's supposed to be a 4, y plus 4 to the third. To get rid of a third power, we're going to take the third root of x plus 6 equals y plus 3. And the last step, let's move that 3 over, and it gives you the cube root of x plus 6 minus 3 is equal to y. And now we can take out the y and we can replace it with f inverse is equal to the cube root of x plus 6 all minus 3. The next step, we're going to verify inverses using compositions. And the rule is if two functions f and g are truly inverses of each other, this must be true. F of g, if you remember compositions, has to equal x. G of f also has to equal x. So you can verify that two functions are truly inverses if f of g and g of f are both equal to x. Let's do that on a few. Number 12. Let's first find f of g. If you don't remember to find f of g, you're going to take f and you're going to plug in g of x. So let's take f, which is x squared plus 8. And in the place of x, I'm going to plug in the square root of x minus 8. When you square a square root, it removes it. That is x minus 8 plus 8 now. Minus 8 and plus 8 cancels and leaves you with x. Then you find g of f, which means you're going to take your g function and you're going to plug in your f function. So g is the square root of x minus 8. And in the place of x, you're going to plug in x squared plus 8. And again, the parentheses here are really unnecessary, so you could get rid of them. Plus 8 minus 8 is gone. Leaves you with the square root of x squared, which is x. So these two functions, yes, are inverses of each other because of these compositions. Next one, let's find f of g. So we're going to take, to find f of g, we're going to take our f function, negative 4x plus 5, and in the place of x, you're going to plug in x over 4 minus 5. When you multiply negative 4 times both of these, you get a negative x, because the 4's would cancel, negative 1 times x, and then you would have negative 4 times negative 5, which is a positive 20 plus 5. You don't have to go any further. These are not inverses because this does not equal x.